Welcome to Shanti-Peace for Mathematics. In this lecture, we are going to discuss regarding a Taylor's theorem and the Taylor's series. So that is the one theorem which is known as a Taylor's formula for Lagrange form of remainder, which tells you that if you have a function f which is real value in the interval a to a plus h such that its n plus 1th derivative are exist for every x and they are continuous in that interval a to a plus h for all n. That means the function has to be continuous as well as its all derivatives up to n plus 1th derivative should be exist as well as their continuous. That means the function should be continuously differentiable function is required. If your x is between a to a plus x, then there will be a c which is between a to x such that fx will satisfy this condition. That means f of a plus f dash of a upon 1 factorial x minus a, f double dash that will represent second derivative divided by 2 factorial x minus a square up to so on, nth derivative of f at a upon n factorial into x minus a power n plus Rn, that Rn is known as a remainder term, and Rn is equal to this n plus 1th derivative at c, where the value of c is between a to x, where x is between these two, upon n factorial into x minus a power n plus 1. So this is known as a Taylor's formula, and after this Taylor's formula will have very important results, that is called the Taylor series of f converges to the function f if and only if this Rn will tends to 0 as n tends to infinity. And the corollary of the previous result, which we can state for if your theta is between 0 and 1. So instead of c, if we can find out some theta as we have in the Lagrange theorem, that c is nothing but the a plus theta h, then the previous formula, that is this formula, is changed to this one, where f we have written from a plus h to f of a, f dash of a upon 1 factorial into h, f double dash of a upon 2 factorial into h square up to so on. And for the particular case, that Taylor's formula will convert to the Maclaurin formula for a equal to 0. So if you can have in the previously, that means in the Taylor formula, if you substitute the value of a is 0, then this is known as Taylor's formula. And the Taylor's formula where you have a is 0 in each step. So based on this Taylor's theorem and Maclaurein's theorem, we'll like to discuss certain examples on that. So here the first example that we like to discuss is write a Taylor's formula of f of x is equal to sine x about x is equal to a in the interval minus infinity to infinity. So as you know that a equal to 0 means that it is the Taylor series is nothing but the Maclaurin series. So here we have given is f of x is sine x, which is in the interval minus infinity to infinity. And we know that by successive derivative, that the nth derivative of this function f, that means the nth derivative of sine x, that we can calculate or we can have, it is sine of x plus n pi by 2. This is true for all x and for all n it is in n, that we already have. Therefore, this nth derivative of f at 0, that means x is equal to 0, if I substitute that will gives me n pi by 2, sine n pi by 2. So what we will have this value, if n is even number, then it will be 0. If it is odd, then it will alternatively plus and minus sign. So what we can observe is this fn at 0 is 0 if n is even, and it is plus or minus 1 if n is odd. It is alternatively changed. That is, you can say that if n is equal to 1, 3, 5, 7 up to so on, then f nth at 0 is plus or minus 1. Hence, by the Maclaurin expansion, or I can say a Taylor series expansion, hence Taylor's expansion of f of x with the Lagrange form of remainder is f of x is equal to f of 0 plus f dash of 0 upon 1 factorial plus f double dash 0 upon 2 factorial into x here, x square up to so on, f nth derivative at 0 upon n factorial into x power n plus Rn, where the Rn will say it is x power n plus 1 upon n plus 1 factorial into f n plus 1th derivative at the point that you can say that a plus theta h. A is 0, so it is at theta h. 0 plus theta h. Now we have to prove that this Rn will tends to 0 as n tends to infinity. So let me substitute this value, that is x power n plus 1 upon n plus 1 factorial. The value of nth derivative of the function f, which is sine, gives you n plus 1 pi by 2 plus theta h, because f n at x is x plus theta h. So here it is, instead of x we have theta h, so that's why it is theta h plus n plus 1 pi by 2 we'll have here. Now let us take what is the mode of Rn. The mode of Rn that we can have, it is mode of x power n plus 1 upon n plus 1 factorial into mode of sine of n plus 1 pi by 2 plus theta h. But this is less than or equal to mode of x power n plus 1 upon n plus 1 factorial. Now we have to see what will be the value of this as n tends to infinity, and I will say that this will tends to 0 as n tends to infinity. To prove that this quantity tends to 0, so to prove that limit of mode of x power n plus 1 upon n plus 1 factorial is 0 for every x as n tends to infinity. Let us see, consider the summation of x power n upon n factorial, n running from 0 to infinity. If I consider this series by ratio test, that is limit of mode of an plus 1 upon an as n tends to infinity, that will gives me limit of n tends to infinity. Here an in this series it is x power n plus 1 upon n plus 1 factorial into an, it is x power n upon n factorial will goes in the numerator, and you just observe that this x power n will get cancel out, left with x, n factorial will cancel out, left with n plus 1, so it will left with limit x upon mode x upon n plus 1 as n tends to infinity, but this will tends to 0. So therefore we can say that the series x power n upon n factorial is convergent for all x. Since it is convergent and we have one zero test for that, if the series is convergent, then nth term of that will tends to 0. So therefore I can say that the limit of x power n upon n factorial as n tends to infinity is 0 for every x. So what we have claim is this quantity tends to 0 as n tends to infinity, that we have proved here, and therefore this Rn will tends to 0, and therefore we can say that the series for hence we get Rn is tends to 0, and therefore the sine x we can write down as f of 0 plus f dash of 0 into x plus f double dash of 0 upon 2 factorial into x square plus f triple dash of 0 into x cube and so on. F of 0, that is sine 0, will gives me 0, f dash of 1, that is a first derivative at 0, that will be cos at 0, will gives me plus x minus f double dash. That we can also obtain from this situation. That means if it is even number, then it will be 0, and it is odd, then it is alternatively plus and minus. So if first time it is plus and then it is minus. So if I can use that things here, then this term will become 0. So it is 0 minus x cube by 3 factorial plus 0 plus x raised to 5 by 5 factorial and so on. So finally the series for sine will get, it is by Taylor series, is this. So similar way I can give you as an homework that obtain the expansion of cos x when x is between minus infinity to infinity. Let us have another example. For x is between minus infinity to infinity, prove that e power x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. So here by looking at this series, we can see that it is a power series of x about 0. So it is actually a Maclaurin series of the function. And here the function is f of x. So here f of x is e power x. And we know that the nth derivative of e power x will be e power x for any x, and for any n it is in n, which we have already known. Now by taking a equal to 0 in the Taylor's expansion or in the Taylor series, we can have a equal to 0 in Taylor's theorem with Lagrange's form of remainder. We get f of x, we know it is equal to f of 0 plus f dash of 0 into x upon 1 factorial plus f double dash of 0 into x square upon 2 factorial up to so on f nth derivative at 0 into x raised to n upon n factorial plus Rn, where this Rn will gives you the f n plus 1th derivative at some point c upon n plus 1 factorial into x power n plus 1 for some c which is in between 0 to x. If your x is positive and if your x is negative, then your c is between these two. So this is the value of Rn. Ultimate goal is to prove that this Rn will tends to 0. Now if I substitute this value of f of 0, f dash of 0, we'll have this is f of x, which we have e power x, is equal to f of 0. That means we can substitute here, that is f n at 0 will have e power 0, which gives me 0 for all n belongs to n. So for all derivatives the function value is 0, so that's why this will gives me 1 plus x upon 1 factorial plus x square upon 2 factorial plus up to so on x power n upon n factorial into Rn, where this Rn will have it is n plus 1 derivative, that is at c. So that will gives me Rn will be e power c upon n plus 1 factorial into x power n plus 1. Now we'll see what is modulus of this Rn. The modulus of Rn is nothing but the e power c is always positive mod of x raised to n plus 1 upon n plus 1 factorial. That will tends to 0 as n tends to infinity. The argument of this x power n upon n factorial is tends to 0 as n tends to infinity. I already given into the previous example. So that's why this Rn will tends to 0 as n tends to infinity. Thus, the Taylor's expansion of the function of e power x about x is a equal to 0 is e power x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial up to so on. So I can say that this Taylor's expansion will converge to this e power x. Now let's have the another example of a similar kind. That means prove that if your x is between -1 and 1, log of 1 plus x is equal to x minus x square by 2 plus x cube by 3 plus x raised to 4 minus x raised to 4 by minus x raised to 4 by 4 to so on. In general term, that should be -1 raised to n into x raised to n upon n and so on. So ultimate goal is to prove this as a series. So here what we can have is f of x, we have it is log 1 plus x. So if I can calculate the first derivative, that is f dash of x, we'll have it as 1 upon 1 plus x. F double dash of x will gives me it as minus 1 upon 1 plus x square. The third derivative is minus 1 into minus 2 into 1 plus x raised to 3. And if you go in that manner, we know the nth derivative of log 1 plus x formula. We already did it in the successive derivative section. If those who have not gone through the videos of successive derivative, the link is given in the description. Also it is available in I button. You can go and watch it. So it is the nth derivative of this one is minus 1 raised to n minus 1 into n minus 1 factorial upon 1 plus x raised to n. So using the Lagrange form of remainder for the Taylor's expansion, we'll have log of 1 plus x is equal to f of 0 plus f dash of 0 into x upon 1 factorial f double dash of 0 upon 2 factorial into x square up to so on nth derivative at 0 upon n factorial into x power n plus Rn, where if I substitute this value of f of 0, that is log of 1 plus 0, that may gives me 1 log 1, which is gives me 0. F dash of 0 is 1 upon 1 plus x, so that will gives me 1 into x plus f double dash of 0, that is gives me that value is here if I substitute at 0, so that will gives me minus 1. So it is minus 1 by 2 x square. Then the next value is plus 1 by 3 x cube and so on. You know that the nth derivative, that is nth derivative at 0, we'll have here if I substitute 0, we'll have minus 1 raised to n minus 1 into n minus 1 factorial. So plus it is nth derivative, so that nth derivative is minus 1 raised to n minus 1 into n minus 1 factorial upon n factorial into x power n plus Rn, where this Rn is as per the formula, it is f n plus 1th derivative at theta h upon n plus 1 factorial into x power n plus 1 for some value which is between 0 to x. Here is theta is between 0 and 1. So the n plus 1th derivative of this function will leads to, ultimate goal is to prove this Rn is tending to 0. So that will gives me minus 1 raised to n into n factorial upon 1 plus theta x or theta x raised to n plus 1 into x plus 1, that is this value. Here I will take h is equal to x. So here I have taken h is equal to x, where h is any value, here is x is also any value. Now this is the f nth derivative of n plus 1th derivative of theta into h, and upon n factorial is already there. So that's why this upon n plus 1 factorial is there. And if you can just see that what is the remaining things you can got from here. So the mode of Rn will be 1 upon n plus 1, because this n factorial will cancel with this, it will left with n plus 1, and it will have x upon 1 plus theta x raised to n plus 1, and this x upon 1 plus theta x is actually less than 1, so that's why it is less than n plus 1 you can have. And this will tends to 0 as n tends to infinity. Now why this is x upon 1 plus theta x is less than 1? Because we know that the theta value is between 0 and 1. So theta x is between 0 and x. If I add 1, then it is 1 plus theta x is less than x. 1 plus x. So that's why this will gives me 1 upon 1 plus x is less than 1 upon 1 plus theta x is less than 1. And the value of x we have, so if I multiply x, this is gives me 1 plus x is less than x upon 1 plus theta x is less than x, and the value of x is always less than 1. That is our situation is given, the value of x is between minus 1 and 1. So that's why if it is x is positive, then we have this situation. If x is negative, then we can use another, due to this modulus, we'll have it as modulus of x is always less than 1. And so this Rn will tends to 0. So therefore, we say that for any case, whether your x is between 0 and 1 or it is between minus 1 and 1, the Maclaurin series expansion for log x, log 1 plus x is 1 minus x plus x square by 2 minus x cube by 3 up to so on. So in this manner, some standard function can be evaluated by the Taylor series expansion. And it is not necessary that every time you will prove that this Rn is tending to 0. Sometimes we'll just accept that if the function differentiable, for any times the function is differentiable, then we should not prove that the remainder term is tending to 0. Without that also we can say that the Taylor series expansion is valid and it is we have. So for that, let us discuss certain examples here. So expand by Maclaurin theorem that y is equal to 10x. As we know that by Maclaurin series expansion, the f of x that we have, it is 10x, is f of 0 plus x upon 1 factorial f dash of 0 plus x square upon 2 factorial f double dash of 0, x cube upon 3 factorial f triple dash of 0, and so on. So this will be the function you have, and this is the Taylor series expansion. So that means you need to calculate what is f of 0, f dash of 0, f double dash of 0, and so on. So to calculate that one, we have y, which is f of x, which is here it is 10x. So we have y at 0 is 10 at 0. The 10 at 0 will be gives me 0. y1, that is sec square x, which will have it as 1 plus 10 square x, which we have it as 1 plus y square. So make it simplicity, I am just converting the function into y. And y1 at 0 will gives me sec square at 0, but sec square at 0 will gives me 1. In fact, I can use also 1 plus y square at 0. Y square, y is also at 0, it is 0, so that's y at 0 it is 0, so that's why it gives me 1. In that manner also we can calculate. Now to calculate y2, that means the derivative of this function, derivative of 1, if we know it is 0, a derivative of y square, it is 2y1. So y2 at 0 will have it is 2y at 0 into y1 at 0. But y at 0 we have a 0, so that's why this value is 0. y3 we can get by using the product rule here. So y as it is, a derivative of y1 is y2 plus 2 times y1 as it is, derivative of y is y1, so it is y1 square. And the y3 at 0 we can calculate using this formula, that is 2y at 0 plus y2 at 0 plus 2 times y1 square at 0. But y at 0 is 0 and y1 square at 0 is 1. So that's why it gives me 2. y4 we can calculate using again by the same manner, that is 2y as it is, derivative of y2 is y3 plus 2 times y2 as it is, derivative of y is y1 and the derivative of this 2y1 square will be 4y1 y2. So y4 at 0 we can calculate in this manner, that is y at 0 this value will tends to 0, y1 at y2 at 0 is also 0, so that is this value is also 0, and this value also gives me 0, so that's why this will gives me 0. y5 we can get, you can just see that if I can combine this two terms, this can be rewrite as y into y3 plus 4 into 2, 6 times y1 y2. So if I apply the product rule for this, for both this function, we can have 2 times y as it is, derivative of y3 is y4 plus 2 y3 as it is, derivative of y is y1 plus 6 y1 as it is, derivative of y2 is y3 plus 6 y2 as it is, derivative of y1 it is y2. So now y5 at 0, let us calculate that. y4 at 0 we have 0, so this value is 0. y3 at 0 is 2, y1 at 0 is 1, so that's why this will gives me 4. y1 at 0 is 1 and y3 at 0 is 4, so that will gives me 6 to the 12, so this gives me 12, and y4 at 0 is 0, so that will gives me 16, and in that manner you can calculate y6 and so on. So if I substitute all this value into the expansion, that is substituting in equation 1, this value in 1, we get nx is equal to 0 plus, that you can see the first value is f of 0 is 0, then it is x upon 1 factorial into y1 at 0 it is 1, x square upon 2 factorial, y2 at 0 is 0, x3 upon 3 factorial into 2 plus x4 upon 4 factorial into 0 plus x raised to 5 upon 5 factorial will gives me into 16 and so on. So if you simplify this, this will gives me x, this will gives me x plus x cube by 3, this will gives me plus 2 by 15 x raised to 5 up to so on. So this is the Taylor series expansion of the function you will have. In a similar manner, let us calculate one more example. Question is, find the expansion of function f of x is equal to log x. So by Maclaurin series expansion, we have expansion is f of x is equal to f of 0 plus x upon 1 factorial f dash of 0 plus square upon 2 factorial f double dash of 0 up to so on. Here we have y, which is f of x is log x, y1 y0 we have log sec 0, we know that sec 0 is 1, so this is log 1 which is 0, f dash x, that means it is y1, we know it is 1 upon sec x into sec x into tan x. So this sec x is cancelled out because the derivative of sec x is sec x into tan x. So y1 at 0 will gives me 0 because tan 0 is 0 since this is tan x. y2 at 0, y2 tan x, we have sec square x, that is 1 plus tan square x, and that we can write down 1 plus y1 square. That means y2 at 0 will gives me 1 plus y1 square at 0. But y1 is 0, so that means y2 is 1. Same manner as we have discussed in the previous one, what will be the y3? y3 is the derivative of this. y3 will be 2 times y1 y2. So y3 at 0 will gives me 2 times y1 at 0 into y2 at 0. But y1 at 0 we have it is 0, so that's why this will gives me 0. y4 at 0, value of y4 as we have discussed in the previous, that is 2 as it is, y1 as it is, derivative of y3 is y3, y2 is y3, 2 as it is, y2 as it is, derivative of y1 is y2, so it is y2 square, and y4 at 0 will gives me y1 at 0 into y3 at 0 plus 2 into y2 square at 0. but y1 at 0 is 0, so that's why this is 0 plus 2 times y1, y2 at 0, the y2 value we have calculated, it is 1, so that's why it is 1, and this will give me 2. y5, it will be 2 as it is, y1 as it is, derivative of y3 is y4 plus 2 y3 as it is, derivative of y1 is y2 plus 4 times 2 y2 y3, and y5 at 0, that let us calculate. Y1 at 0, we have it as 0, y3 at 0 is 0, and so this will give me y5 is also 0. y6 can have, that we can write down, this is 2 times y1 y4 plus 6 times y2 y3. So it is 2 times y1 y5 plus 2 times y4 y2 plus 6 y2 y4 plus 6 times y3 y3. Now y1 at 0, it is 0, so this term is 0. y2 at, so it is, this term will get, that means y4 at 0 will have 2, so it is 2 is already there, so it is 2 into 2, and y2 at 0 is 1. This is also gives me 6 into 2 into 1 plus y3 at 0 is 0, that we already have, so that's why this is 0. So that gives me 4 plus 12, that is 16, and in that manner you can calculate the further values. Therefore now, substituting these values in f of x, we get log of x is equal to 0 plus x upon 1 factorial into 0, that means y1 at 0, plus x square upon 2 factorial, y2 at 0 is 1, plus x3 upon 3 factorial, y3 at 0 is 0, plus x raised to 4 upon 4 factorial, y4 at 0, y4 at 0 we have it is 2, so that is 2, plus x raised to 5 upon 5 factorial, y5 at 0 is 0, y raised to x raised to 6 upon 6 factorial into y6 at 0, y6 at 0 we have got 16, and so on. So finally the answer you will have, it is x square by 2, that is this, x raised to plus x raised to 4 upon 12, because 1 2 is cancelled out and we will left with 4 3s are 12, plus x raised to 6 upon, here it is 16, so 4 is cancelled, 2 is cancelled, so it will left with 45, and so on, and 2 is also cancelled. So this is the answer for expansion of log of x. Then let us do the next question. Expand cos x in powers of x minus pi by 2. That means we need to find out what will be the Taylor series of cos x about pi by 2. By Taylor's expansion, I can say Taylor's theorem, we have f of x is equal to f of a plus f dash of a upon 1 factorial into x minus a plus f double dash of a upon 2 factorial x minus a square to so on. Here a, the value of a is pi by 2, so that is in powers of x minus pi by 2 you will have. The function f of x we have given, it is cos x. Now we need to calculate what is f of x is equal to cos x. As f of pi by 2 first we need to calculate, that is cos pi by 2. Cos pi by 2 is 0. Of f dash of x, that is minus sine x. F dash at pi by 2 will be minus sine pi by 2, gives me minus 1. Double dash at x, that will be minus cos x, that f dash double dash at pi by 2 gives me minus cos pi by 2, which gives me 0. F triple dash at x will have it as x, is f triple dash at pi by 2 gives me sine pi by 2, which has 1. Fourth derivative will be cos x, and at pi by 2 the cos pi by 2 is, we know it is 0. Fifth derivative will be minus sine x, so that will gives me at pi by 2, it is sine pi by 2 minus, So that's why this will give me minus 1. So in this similar manner, we have all the derivatives value, and we are substituting this value, get this into this equation. F of x is equal to f of pi by 2 plus x minus pi by 2 upon 1 factorial f dash at pi by 2 plus x minus pi by 2 square upon 2 factorial f double dash at pi by 2, and so on. So as we have discussed that f of pi by 2 is 0, so that's why it is 0 plus x minus pi by 2 upon 1 factorial f dash at pi by 2, it is minus 1, plus x minus pi by 2 square upon 2 factorial f double dash of pi by 2 will be 0, plus x minus pi by 2 cube upon 3 factorial f triple dash, that means the third derivative at pi by 2 is 1. We have calculated x minus pi by 2 raised to 4 upon 4 factorial into 0 plus x minus pi by 2 raised to 5 upon 5 factorial, and the fifth derivative we have already minus 1, and so on. So the final answer from this, it can be say that it is x minus pi by 2 minus sine plus 1 by 3 factorial x minus pi by 2 square cube minus 1 by 5 factorial x minus pi by 2 raised to 5 up to so on. So this is the Taylor's expansion of cos x in powers of x minus pi by 2. So in that manner you can find out the Taylor's expansion of any function in any power. Next example I am giving you as a homework, that is expand x cube plus 7x square, x cube plus 7x square plus x minus 1 powers of minus 1. This is your homework for this video. You complete it, and the hint is this expansion contains only finite terms of that series. That's it for this video. If you like this video, please press the like button. If you have any comment, suggestion or question, please drop down in the comment box below. See you in next video. Till then, bye bye, sayonara.